Everyone, I am Evan, and I'm going to talk about GOSIM, which is a Rust framework for building application AIs, and a little bit more about how to generate types from language models. So first, a little bit of backgrounds. GOSIM is an application framework for AI. It supports over 35 different models and 5 different modalities within that. It runs models locally, so you don't have to worry about expensive cloud bills or connection issues. And since everything is local, you don't have to send data to servers that you might not trust with the data. So it's great for privacy on data as well. GOSIM integrates with a bunch of different data formats and other libraries in the Rust ecosystem. So it's easy to load documents that you have access to and use those as context for your language models tasks. GOSIM is focused on end user applications. So it's focused on pipelines, not just models. So instead of just giving you a model for transcription, GOSIM will take you from recording audio from your laptop to feeding that to a transcription model and then getting a stream of async text out. It has pipelines for transcription, tasks, chat, search, and a bunch more. And all of the models in GOSIM are fully typed. So it doesn't just output the modality that you normally have for the model. So for text generation, it doesn't just output text. It can output whatever type you define. So if you want to use GOSIM for a task like agents, where you need to use the language model as like the first step within a chain, it's great for that. There are 3 basic components for an AI application. You have some context, which is going to be documents, your microphone if you're recording audio, transcriptions, or some files like recordings. Then you have your model, which could be a language model. It could be a transcription model like Whisper, or embeddings for search, image generation like Stable Diffusion. Then you get some sort of output. Normally that's going to be determined by the model, but in GOSIM you can insert extra information into the model to tell it to output a specific type. So text generation models, large language models like ChatGPT, normally just output text. But with GOSIM, you can use a parser to force the model to generate a specific form of text. So instead of getting out just text, you can get out a specific structure, like a name of a speaker with more information on the speaker, like their age, a description, etc. And you're always guaranteed to get that specific format, which means you can always parse it into the type you give it. So in this talk, I'm going to guide you through using GOSIM and a little bit more about how GOSIM works under the hood through a scraping task. So when you looked at the GOSIM conference, you probably took a look at this page. This has some of the information from the talks page, and it has a description of the schedule with different talks, the speakers, the titles, and a description of the talks. We're going to be grabbing information from that page and then turning it into JSON information we can use in other applications. So in our diagram, the input here is the HTML talk information from the website. We're going to pipe that into a language model. And then instead of outputting just text, we're going to output a list of talks with the title, time, and description of the talk. Before we dive into getting that task working, we're going to talk a little bit more about how language models work under the hood. So here's the general language model pipeline. There's going to be 3 large sections we need to focus on here. So first, you start with some text. That gets tokenized into an encoding that the language model understands. The language model runs. It generates next token probabilities. And then the sampler runs to choose from those token probabilities, which is then added to the text. And you repeat the process until you get as much text as you need. So the first part that's important here is turning that text into tokens. So language models don't view text directly. They don't view bytes or characters or words. They view tokens, which are about 2/3 of a word, but it depends a lot on the language you're using and how common the words you're using are. So in this example, how do language models view text? Each of those words are tokenized as 1 token. But if you have a less common word like GOSIM, that is tokenized as 3 separate tokens. And underneath, you can see the token identifiers that each of these tokens correspond to. That's a little bit closer to like how the language model views the tokens, because they don't have the original source text. They learn to associate different tokens with each other, and that's how they model language and predict new tokens. So next we have inference. After we have all those tokens, we feed it into a language model, and we get a whole bunch of probabilities out. How the language model works isn't going to be important for this talk, so we're just going to treat it like a black box. The language model gets tokens in, and then it predicts what token it thinks is most probable next. And in this case, it thinks language is the most probable token to follow from that text. And can is also very high, what, how, and goes on from there. And there's a bunch more that we don't show. After you have those probabilities, we need to choose one that we're going to add to our sequence. This process is called sampling. And it doesn't always choose the most probable token. It takes the list of probabilities and it filters it through an algorithm that generally looks at like what the last couple tokens were, just so it doesn't repeat itself a bunch. So if you always choose that most probable token, you're going to get very boring text that generally repeats itself. So here it might do, how do language models view text? And then repeat itself again, how do language models view text? If you let it run by just choosing the most probable token. Okay, so now we know a little bit more about how language models work. Let's run our task, which is getting some information from the GOSIM website and turning that into JSON. So here is the Rust code using GOSIM that runs our task. So we're going to use a async function as our entry point, load a new Llama chat model. Llama is a little bit like ChatGPT, but it runs locally and it's open source-ish, so you can use it in commercial applications without paying for a license. Then we're going to include a description of the task, run our task, give it a few examples to give it more information about what task we want it to do. And that will just be like a talk and then the JSON we want out. And then we're going to do task.run with the entry from the website. Then pipe it to stdout and we'll just display on the screen. So here's the information we get out. It gives us something like JSON, but it isn't exactly right. We have a whole bunch of empty fields here. So description on 3 of these talks is completely empty, even though the text we gave it has a description. And then the last talk has even more issues. The time is in entirely the wrong format, and it's missing a speaker field. So this clearly won't do. Just asking the language model nicely to output a specific format isn't working. We can give it a little bit more information about what format we want with a parser. So in between, when we have the next token probabilities and the sampler, when we're choosing what token we want to generate next, we're going to add a parser that knows where we are in the format. So instead of just generating text, we're now generating a very specific sequence of text. And our parser has a couple more requirements than you might see in a normal parser. First, it needs to be incremental. We run this parser a whole lot of times for every new token. A language model like Llama has a vocabulary size or a number of tokens that it can generate of about 250,000. So we need to run the parser on each of those 250,000 possible new tokens and then check if they work. And if they don't, we want to roll back and continue with the token we did choose. So instead of reparsing the entire old text, we need to be able to continue where we left off whenever we add new text. We also want to fail fast. So instead of parsing a couple tokens and then checking if it parses, we need to fail as soon as possible so we avoid loading more tokens into the language model than we need to. One parser that works really well for this is regular expressions. If you haven't used them before, they accept a pattern and then it generates a whole bunch of states and the parser moves between those states based on the character it's currently at. This is great for our use case because moving between states is very quick. It can be incremental because we can always roll back to a previous state, and it always fails fast. So here is a regular expression that accepts whole numbers that are larger than 1. And you would start at the start state, and we see a character between 1 and 9, go to the middle state, repeat for as many times as we want whenever we see a 0 or a 9, and then we end the file at some point. So if we ran our language model with this filter, it would only generate the tokens on the left, and it would reject all of the sequences on the right. And here's a regular expression for our task. It isn't the prettiest thing in the world. That's some ugly JSON there, but it does work. So here is what one example would look like with our language model. So we have our language model, we generate next token probabilities, and then each of those tokens get filtered by if it is accepted by our regular expression. So here, since we're at the very beginning of the sequence, the only valid token is going to be an open curly brace, which starts the JSON object. And all of the other tokens get eliminated, and we don't even sample them. And the only one left is the open curly brace. Here's what a task looks like when we run the model, and this looks a lot better. We have the title, time, and description for every single speaker, and all of the fields are full as well. There's still a little bit of odd text, like description always ends with a spacebar, but we can fix that with some tighter constraints on the model. If we tell it that the last character can't be a spacebar, it won't end with a spacebar. Regular expressions can be kind of tedious to create and maintain. They end up being like quite long, and they're also very limited, as we'll find out more later. We can use a Rust macro to generate the regular expressions for us. So instead of typing out that whole regular expression and testing it with a couple of test cases, we can just add this annotation to the top of our struct with derived parse, and then GOSIM will figure out what kind of parser we need from the data. This also has the extra advantage of getting typed data out of the language model. So instead of just validating the text as we generate it, this is going to parse it and then return the parse results. So at the very bottom there, you can see let structured is a type of talks. And that means that as we get the language model output, it is actually of type talks instead of string. We annotate some of the fields with a little bit more information about what kind of expression we want to accept. So you can see like parse pattern accepts only a regular expression that fits that pattern. And then the rest of the fields are mostly unannotated because we don't really care as long as it fits the type of string or list. You might have noticed something interesting about the probabilities we looked at a few slides ago. Since there is only one possible token that the language model can generate, these probabilities here are not actually that useful. Instead, we can just skip running the language model entirely and accept the only possible token. So here at the very beginning, you can notice it jumps forward a few tokens. It has the opening curly brace, the quotes, and then talks. Those are all loaded at once without looking at the language model at all, because our parser said that those are the only possible tokens. This will speed up text generation because we don't have to run the language model as much, which is really nice for heavily structured things like JSON. To view a little bit more what that looks like in terms of a language model, I have a demo application here. So here we're going to be acting as a language model. We have this regular expression up here that defines the structure we will accept. And the very first part here is the part that the parser already knows it will accept. So here we don't have to choose anything. So the only option is talks, and then the array start, and the object start, and then title. And if I type in a title like hello world and in the quote, then it will complete for me the next part of the sequence that is forced. So here, time isn't something I can change. I can enter a time like 12 p.m., end it, and it keeps completing. So here, there's a whole bunch of tokens that I don't have to enter as the language model, and that saves us a lot of time when generating. Okay, so now that we have our JSON data from the website, we can use that data for a bunch of different tasks. We can make a database out of that. We could filter based on the name with a search tool. We could sort by time or other metrics, or we could use more structure generation to generate UI based on that data. So here we're going to be using a language model to take the JSON talk data we had from the previous step and generate a personalized talk summary using HTML. It turns out HTML is a little bit more complicated to parse than our regular expression from before. Our regular expression is a regular language, which is great because they're really fast and they use a fixed amount of memory for each state. So no matter where you are in the text generation, you only have like however many bytes of memory. It doesn't ever grow. But HTML is more complex and it needs a context-free language, which has unbounded memory. Because for HTML, we need to keep track of where we are within the HTML. We could be inside a div, which is inside of the list, which is inside of a table, which is inside of an input, and we need to know to close each of those tags. So that has unbounded memory. It's going to run a little bit slower, and we can't use regular expressions to define it. Instead, we're going to use a trait, which lets you run whatever Rust code you want as the implementation, and then that will be used as our parser, which will filter the large language model output. So here our trait takes a parse method, which returns either the new parser state, a result of the parser, which is going to be like whatever the output is, or an error if the parsing failed. And we need the new parser state here because if we parse some token like A, then we need to be able to try to parse B and then go back to A if it fails. So that's the incremental part of the parser. You usually don't have to define this trait yourself in GOSIM because there are a bunch of built-in types and combinators you can use to combine them. So GOSIM can already parse integers, floats, strings, regular expressions, and a whole bunch of other sequences. And then if you have a sequence of those you need to combine, you can repeat them, choose one or the other, or combine them in sequence. Here is a snippet of what parsing HTML might look like in GOSIM. We have a full crate that derives the HTML from the HTML spec, which is a little bit longer than this. But here's the basic concept of parsing a div. So you have some literal parser, which parses the start of the div, and then you parse the div attributes, then the end of the div tag, as many children as you need, and then you close off the div tag. You can imagine the same thing for lists and tables and all other HTML tags. Then you just combine those all with an OR, so you could parse a div or a table or another HTML tag. Okay, so now we're going to take our parser and insert that into the language model task and run it to generate some HTML that is always going to be valid. So we're starting a new llama model. We build a parser from element new parser, and then we're going to accept as many elements as we want until we see a new line. We define the task with a couple of examples, a description like before, and then we run it in a loop with some input about what we want the UI to look like, and then a little bit of data from the last step. We're going to write it out to a file and view that file in the browser. So here's one example of what that might output. Now this is not as pretty as the GOSIM website actually has, but you can imagine filtering all this data on information that you know about the person who is viewing it. So if I'm interested in Dioxys, I might see only the talks by Jonathan and Nico instead of all the other talks. Or I could color those in different colors, filter out the titles, and just view the speakers and description. All right, so here is the application running. It's going to generate a table with just the title and the time instead of the talk descriptions and the speakers. And it's going to take a second for it to load the information. And then after it loads the JSON information that we generated from the last step, it will start streaming in the result as a HTML table in the bottom right hand. So we can see the time and title streaming in, and then each of the talks come in. So you can create like bespoke UIs based on information that you only have right as the user is viewing the page. So that's a little bit about what GOSIM does today, but there's also a bunch of plans for future work. Right now, GOSIM only supports creating parsers and running language models in Rust, but I would also like to support TypeScript, Kotlin, and Swift in the future. These are great because a lot of applications are built in those languages, and GOSIM would be useful there, so you can ship more applications that use local language models. And then next, I'm also working on faster and incremental tokenization. So one of the slowest parts of generating text with language models that are small is taking the text and generating the tokens we saw at the beginning of the talk. Part of the reason this is slow is because traditional tokenizers are not incremental, so you have to re-tokenize a bit of the old text before you see what the new text is tokenized as. There's a different way you can formulate the problem that runs quite a bit faster, and it lets you do incremental tokenization. So as you stream in text, you can also stream in the new tokens. And that will be shipping in the next release. And then I'm also working on parser augmented models. So right now we have the language model running here, and then we filter the output with a parser and generate new text. The language model could have more information about where we are in the parser if we provided it. So for example, you might be generating a string, and the language model thinks it's generating a number, so it starts generating the number, and it can like run on for quite a while if it doesn't know how to end the sequence. So we can feed in more information about where we are in the parser to the language model. That should hopefully improve performance for some of these longer parsers. That is all I have for today about GOSIM. If you are interested in using the project or you want to reach out, you can scan the QR code, and it has a bunch of links.